Okay, so let me move toward the slides. Okay, so today we are going to, you had the chance to look at the decision-making process, a process that consists of 6 steps after defining the problem and looking at the objectives and defining the alternatives. You look, of course, at the possible consequences. At some point, however, you have to make a choice. So you have to decide which of the alternatives is really the right one. In many scenarios, it might be very simple. You can just have 3 alternatives, and you have also the metrics of how good the 3 alternatives meet the objective. You choose one. So enumerate, choose one. In some other cases, the choices might, however, be very complex. There might be a time structure. So there's not only a one choice to be made, but a number of choices. And in this case, you could think of methods and tools that could support that. An important element is, of course, the sensitivity analysis. Today's webinar will focus on the last 2 points, making a choice and performing sensitivity analysis. So actually, 2 elements will be discussed. We start with talking about decision trees and move on towards linear programming. I really want to make it as applicable as possible, so I rather avoid creating a very solid foundation for the tools I'm presenting. And let me start with an example. This example is about a firm considering production of a new electronic book reader called Nook. The firm is called Barnes & Noble, an actual firm, and the scenario could have been considered at the company in the year 2012, but this is not the point. The point is that we have a decision problem of a firm that can produce the e-book reader. And of course, in order to produce it, they have to produce, or they have to create a plant, because they don't have enough capacity, and they have a choice between a large plant and a small one. And their decision will depend on some uncertainty. As it's usual, you don't know what will happen in the future. You have some guess or estimate of the market. It might be, in this simplified scenario, a favorable market or unfavorable market, and depending on the choice of the plant, a big one will be very profitable in a market that is favorable. The firm will get a net profit of 200,000, or in an unfavorable market, it will then cause a big loss of 180,000. A small plant, in contrast, will have a net profit of 100,000 in a favorable market, but a smaller loss, a small plant of 20,000. Now, of course, the question one would need to ask is, which plant, if any, should Barnes & Noble construct? So the usual approach, and this is the thing that you have looked at already in the first week, you look at the problem, you define it, you think, okay, what the goal is. The goal is profit maximization. What are the alternatives, the different sizes of a plant, what is the uncertainty involved, and what are the possible outcomes and consequences. Usually, with this amount of information, you start, or you try to find the best decision. If the decision includes a number of decisions, I will talk about it as a decision policy. This becomes clear in a moment. A very useful tool to support the decision-making process are the decision trees. So we start with modeling the decision scenario, and only then we look at the possible solutions. So first, model it. here you have an example of a decision tree, a small decision tree, and some explanation for the element. The light blue square means a decision. At this point, a decision maker decides between alternative 1 and 2. The dark blue circles is uncertainty. So what's going to happen in the future? Here we have states. We can have a number of states, and for every path, so for every single path, starting from the first node to the last, we have an outcome, and this is denoted by a orange triangle. And the orange triangles are associated with the payoff we will look at. This is something that makes more sense if we really apply it to our specific problem. So we go back to the decision of Barnes and Noble and try to create a decision tree. So there is the blue square, and it says that the firm can either construct a large plant, construct a small plant. Good. This is what the description said, but in fact, the firm can also actually not do nothing. So in this case, it means they don't construct any plant at all. And this is also an alternative. You have to list all possible alternatives. In more complex problems, you list all relevant alternatives, because otherwise you wouldn't really move forward. Now, when we have the first decision, what comes afterwards is the uncertainty about the market, and the uncertainty about the market is in form of the dark blue dots, and this is the unfavorable market or favorable market. Here the important thing in the picture is that you start from the left, move towards the right. The left means earlier, the more to the right it means later on. When we have the different states on the world, let's say, of the market, we have to also assign the probabilities. In this example, it was 50% that the market will be favorable and 50% that it's unfavorable. How should we think about the two states of the market? We can think about it in terms of knowledge. You have two possible outcomes, and if you don't know anything about the probabilities of occurrence, you have to assume that they're equally likely, so we have 50%. So this is more about the state of your knowledge about the development of the market. Now, when we have the tree, we have to keep in mind that the events that we look at have to be mutually exclusive and collectively exhaustive, meaning mutually exclusive means if one happens, the other cannot. So we cannot have a situation that favorable market and unfavorable market, they are true or happen at the same time. And collectively exhaustive, it means this is all that can happen. The last thing that is missing in our picture are the payoffs, and the payoffs are the way to measure to what extent the objective is realized or achieved. Here in this particular case, it was net profit of 200K for the case of constructing a large plant and when the market is favorable, and you can see also the remaining ones. They are also stated over here, these orange numbers. Now, we managed to create or represent or depict the decision problem in a nice graphical way. But now the question about finding an alternative, the right alternative, pops up. So here we of course have to assume something about the objective of the firm. It said at the very beginning that the firm is maximizing profit, or at least the profits were stated, but whenever we have to do with uncertainty, we have to kind of propose a rule that includes the probability. So we will assume that Barnes & Noble is a firm that is maximizing expected monetary value of the alternative. What does it mean? It means that for every decision alternative, for constructing a large plant, we calculate the average monetary payoff, which is 50% of 200K plus 50% of the loss of 180K. It gives us an expected monetary value of 10,000. In contrast, the small plant has expected monetary value of 40K, and the last option, no plant, it has 0. Keep in mind, I assume the 0 over here might be different when we have a more complex scenario, or we know more about the situation. So if the firm is maximizing expected monetary value, the best choice is the small plant. Okay, so what about the situation that the firm is not maximizing expected monetary value? In other words, if the firm is not risk neutral, meaning like most of the people, and we observe it looking at the insurance industry, people tend to avoid risk. They actually are ready or willing to pay to avoid risk. And we can have different possibilities or different risk attitudes. We typically talk about risk-averse individuals, so those who try to avoid risk, and risk-lovers, so those who actually are happy to take risk. If you think about casino goers, then you have the situation of casino goers who take the risk. So there is like, on average, they will lose, but they go anyway. If you look at this particular example, we have to look at what is called risk profiles. So we don't see the average, as in the case of expected monetary value, but we do see the gains and losses. When you see here the example, you see the green ones are what they can gain, and the red ones what they can lose. And we can actually ask how would the risk-averse decision maker choose over here. So let me send you the opinion poll and see how you respond to it. I hope you can see it. Okay, so we have 10 responses, and almost half of it will say no plant, or let's say small plant. The results are changing. So most of you decide to have a small plant. I stop it over here, so if somebody did not take part, don't worry about it. So what we see is, they give different answers, and actually it's not a surprise, because what we have to look at, in this case, we have to look at specific definitions of definition of risk aversion. So there will be someone who will be more risk averse than someone else, and I would like to look at the example of an extremely risk averse firm that will actually minimize the potential loss. So the way to look at it is they see each alternative in terms of what can they lose. This is the only thing that they see. They can lose 180K for a large plant, 20K for a small plant, and lose nothing in the last case. If this is the case, if this is the individual, then the best idea, the best choice would be not constructing the plant at all. But again, here we have to be more specific, and everybody would have a different argumentation for it, probably. Like the risk attitudes also, or the extent of risk attitude will differ across different individuals. Looking on the other side, we can ask the question, what would a risk lover choose? Here the situation is like a mirror reflection. Now again, number of options are possible. I could say that the risk lover looks at just the upside potential. So the constructing a large plant, the focal point is the payoff of 200K, for the small plant 100K, and 0 in the last case. Here, a risk lover would go for the large plant. One small comment is most of the cases is somewhere in between the two types that I have introduced, so you can also observe a number of different risk choices. So this is what is clear, or should be clear right now. When we talk about the decision, even though the decision has been defined in very clear terms, in actual or real-life situations, the payoffs on the one hand, the probabilities on the other are estimates. So we don't really have a certainty that this is exactly what we will get in the future in terms of net profit. This is also not clear whether the 50% it is the actual probability. So sensitivity analysis would help us to look at what happens if the estimates are imprecise, if they change a bit. So this is a very important element of every decision analysis. And I would like to show you the two cases, what is meant by that. And one question one could ask in the case of sensitivity analysis for payoffs, we could say, how large should the payoff or the net profit from building a large plant in a favorable market should be in order to make this one an optimal decision. I go back to the case of expected monetary value maximizer. So we have a risk neutral Barnes & Noble over here. And how do we calculate it? We know that the expected monetary value for normal plant and small plant are 0 and 40K respectively. And the expected monetary value for a large plant will be a function of X. We don't know X. But you should be clear that this is what we get. So the question that we are asking is, for what value of X is the expected monetary value from a large plant greater or equal to the expected monetary value from a small plant? We solve a system of inequality and get the answer that the net profit would need to be at least 260K to make a large plant an optimal decision, an optimal or the best alternative. And so what do we do with that? You always have to think in terms of probability. So how much more is it than it is at the moment? We have 200K at the moment, current estimate. It would need to be 260, which is 30% more, probably unlikely scenario. So you know that the current decision or choosing a small plant is not so vulnerable or so sensitive towards the change of payoff of a large plant. Another question that could be asked is a question about the sensitivity analysis for the probability. And here we do a very similar analysis. In this case, the probabilities are the same for the favorable and unfavorable market, but instead of using the 50%, we'd rather say a P. So for what probability of unfavorable market, P, would Barnes & Noble prefer to build a large plant? So how much away are we from the case? So the same situation happens here. We can calculate the different values, and we need to compare the expected monetary value of a large plant with a small plant. And what we get also, again, a comparison function of P, and says, if the probability of unfavorable market would be 38.4% or smaller, then a large plant would be the optimal decision for a risk-neutral Barnes & Noble. So we have about 11.6 percent points lower than the initial estimate. Rather a big difference, so we could conclude that the actual analysis is pretty robust. Now, this is what we can do with the sensitivity analysis. In a more complex problem, the calculation will be more involved. However, at the same time, you can always you have to keep in mind that whenever we do sensitivity analysis, we change one parameter, keep others constant. So this is the way it works. In many situations, as managers, you face a case that you could add some information. You could purchase some information if it's available, and this is the situation where a manager decides to run a market research project or or like buy some database or information about customers. But whenever it's done, a question must be asked: what is the value of the information? Is it greater than the cost? Whenever the cost, its cost is always clear to say because you pay a price for a research project, for a data bank. But the value, how do you calculate the value of information? Here, depending on the comparison of cost and value, you decide to purchase it or not. I will look at two elements. On the one side, we look at the expected value of perfect information and expected value of sample information. This follows. So what is expected value of perfect information? So perfect information is a rather theoretical construct, an idea that all the uncertainty in the problem, decision-making problem, is resolved. So this disappears. So if you could get to a situation like that, what is the value of it? How much more can you earn when this happens? So this is the amount of money somebody will be willing to pay is up to the expected value of the perfect information. When you look at it from a broader perspective, then if you consider any information, whether perfect or imperfect, imperfect means it resolves some uncertainty but not all the uncertainty, then the value of any information should be smaller or equal to the expected value of perfect information. Let's look at the case of Barnes & Noble, and I will explain how to calculate it on the next slide. So what we will do, we reformulate the decision-making problem, and we say how much should Barnes & Noble, or should they run, or should they buy the information or not? If they don't purchase the information, so we have one alternative. Purchasing the information is another one. If they don't purchase the information, nothing changed, right? So we have exactly the same decision tree as we had before. However, what happens if they purchase the perfect information? Pay attention to the order of nodes. So we have the uncertainty is before the decision. So if they have perfect information, they know whether the market is favorable or unfavorable, and only then decide what to do. Okay, so this is the way it's constructed. The payoffs are as they were before. So on the lower part of the decision tree, we know that the best alternative, going from the backward induction, we know that running or building a small plant is the optimal decision. However, if we now look in the upper part of the tree, in a favorable market, what is the best that the firm could do? We have to compare large plant, small plant, and no plant. We know that the highest payoff is for a large plant, and therefore this is the best alternative. For the case of unfavorable market, the best outcome is for not building a plant at all. Now we have the two alternatives, so we know what the expected value of the decision is, and we go backwards. So we look at the uncertainty coming from the market, whether favorable or unfavorable, and see that the expected monetary value of perfect information, which is the value of 200K and 0 with equal probability, is $100,000. So if they purchase perfect information, the expected monetary value will be this. If they don't purchase perfect information, it's 40K. 40K is on the lower part, and it's 40K, and the value of perfect information is the difference between 100 and 40. This gives us 60K. Any information that Barnes & Noble would be offered, they should not pay more than $60,000. The other case is the situation of imperfect information, and this is a more realistic case. When you run a market study, you resolve some of the uncertainty, but not all of it. So the imperfect information could also be an educated guess or imperfect testing. So you, in fact, like in medicine, you approach a patient, do some testing, but the testing is imperfect. So you learn something, but you don't learn everything about the possible disease of a patient. This is could be also here. Independently of whether it's perfect or imperfect, the same question should be asked: what is the value of imperfect information, and what is the cost? If the value is greater, go for it. If greater than cost, otherwise leave it. So the way to do it, we again rephrase or reframe the question, and we ask the question: should they purchase the imperfect information, or shouldn't they purchase perfect information? And before discussing, I just go to the case of Barnes & Noble. We expand the case, and now we have the production decision, including market research option. Barnes & Noble could run a research project. It costs $10,000, but the research project will not really say the market is favorable, or will be favorable, or won't be favorable. What it does, it will provide two answers. We simplify it, but we say the report, the outcome could be either positive or negative. And given the past experience, you know that one happens with already 45%. This is positive, and 55% is negative. And what it does, it helps you with getting the probabilities better. So you have more information, and if the result is positive, then the probability of having a favorable market is 78%. And if it's negative, the probability of favorable market is 27, so it goes down. The questions to be asked is: should they commission the survey? If they do, what decision should they do in terms of size of the plant, or what decision should they make if the result is positive, and what should they do if the result is negative? Here we have an extra contingency. Something will happen in the future and can be observed. And if can be observed, it has to be taken into account in the contingency plan. Now, like in the previous case, here no survey means no change to the decision-making problem. So this is as it was before. If they take the survey, there will be some uncertainty whether the result is positive or negative, and the decision has to be made afterwards. So should they build a plant small, big, or none at all? And the important thing is that what happens afterwards. So the probabilities changed. We said if the probability, or if the result of the survey is positive, the probability is 78%, 22% in unfavorable market. And what also changes are the payoffs, because we have to subtract the $10,000 the cost of the market research project, and this will be the same in the case of a negative result of the survey, but the firm paid the $10,000, so it doesn't. The payoffs are the same, but the probabilities will be different. Okay, so what it does, because I can imagine that you don't feel very easy about the idea that we get here. Of course, the precise numbers these are estimates, and more importantly, what the survey does, it shows you the correlation. It shows you correlation between the outcome of the survey and the actual situation on the market, and this is something that can be well accepted. So, how do we cope with this case? I will be rather quick over here because we again would like to calculate the expected monetary values and decide what is best when the positive result appears, given the expected monetary value criterion. It's best to build a large plant. It's best to build a small plant if the result is negative, and if there is no survey, build a small plant. Now, what is the next step? We have to see what is the expected monetary value of the survey. So we look at the probabilities of the different market outcomes, or say survey outcomes. It's 49.2 thousand, and if the survey is taken, or if there is no survey, is 40,000. Here, the decision of a risk neutral Barnes & Noble is, of course, to take the survey because it brings a higher expected monetary value. So this is the answer, but I would like to test your understanding and provide you the following poll. So, what is the maximum price Barnes & Noble would be willing to pay for this particular market research survey? Okay, so we have some answers. All the options were taken, so to speak. The correct answer, maybe I give the chance to all of you to participate. Okay, so I stop over here. If some of you couldn't take part in it, don't worry so much. The correct answer should be at 19.2, because recall, we have here the price of the research project, so we already paid $10,000, and there is still 9.2 thousand left. So in order to have the maximum price, or the value, expected value of the imperfect information, is exactly the difference. So it's 19.2. I hope this is clear right now. Here I would like to skip it, this part, because it actually relates to the chapter, to the first section of the course, where about the common errors in decision making that you are probably familiar with, is the sunk cost fallacy, hidden cost fallacy. But I would like to emphasize that also here in this type of analysis, one should not exclude the subjective or non-monetary costs. So if there is some costs that may in effect on the people that work for you will not have monetary effect, but they have health risk, this should or could and should be taken into account. Now, when I look at the time, I see that actually it took a bit longer than expected, and I'm just thinking how to proceed. I can briefly start maybe with the topic, and I will stop when it's convenient. And you can just look at the slides. I have uploaded them, or we just take a few more minutes. So we will see how it goes. So the second part that is interesting is the linear programming that you could use in solving problems. Actually, we talk about problems that are big in the sense of many alternatives, and you cannot do it, select one particular alternative. So here I have prepared an example, a brewery problem, and a brewery is producing two sorts of drinks, ale and beer. If they do it, they need some resources, so they need corn, hops, and malt. And the different beverages, they need also different recipes. The table over here shows us the different shows you the different ways to produce it. So the table says if you want to produce ale, you need to have 5 pounds of corn, 4 ounces of hops, and 35 pounds of malt. And the profit from a barrel of ale is $13. The same thing you can say is for like different recipes, but the same logic is for beer. And you have a limited amount of resources. It's 408 pounds of corn, 160 ounces of hops, and 1,190 units of malt. Of course, there will be other ingredients. You know, you need water, but water is unlimited here, so we don't have to worry about it. The question that the brewery could ask is, how many barrels of ale and beer should the brewery produce to maximize profits? Here, an implicit assumption is whatever they produce will be sold. So how can we solve this problem? It's certainly not an obvious case, but how can we actually solve problems of this sort? The answer is you can use computers to do so. However, before we can implement the problem in a computer, we have to understand how to do this, and this is what I will start with. And we can build a linear program, and we ask first, what are the variables? So what are we changing? So what is the thing that we are changing? So the amount of barrels of ale and beer. So A and B will be our variables. And the thing that we want to maximize is the profit. So $13 per barrel of ale plus $23 per barrel of beer. We sum it up and maximize it. We will have also constraints for the 3 ingredients, and this is also in the upper right corner that you can have a look at it. It basically says for corn 5 pounds for a barrel of ale plus 15 pounds for a barrel of beer. Depending on A and B, you have to produce less than 400 or use less than 480 pounds of corn. We also use the non-negativity constraint, so A and B should be positive. Now, let me test your understanding, or if you are not familiar with mathematics, what could be helpful over here is the following. Let's look at the problem from the perspective that only ale is produced, okay? What does it mean? That beer, so B, is 0. If B is 0, then we can produce how many barrels of ale? We can produce 480 over 5, so 96 barrels of ale if we look at corn. For hops, it will be 40 barrels. If we look only at malt, it's 34. So if we take all the 3 constraints into account, we have at maximum 34 barrels of ale. So the profit will be 442. How do we get it? It's 13 times 34. If we only look at the situation that you produce beer, you should be able to test your understanding. Then we can produce at most 32 barrels of beer, and the profit will be 736. You can, of course, think of some mix. And if you mix it, you can think of 12 barrels of ale, 28 barrels of beer, and the profit will be 800. Okay, we can model it, still we don't solve it. And it's important that you develop an understanding of the problem, and usually it's represented graphically. So I will look at the elements of the mathematical model, I will look at the constraints first, and then at the objective function, so the profit function, and show it graphically. If you try to represent the production plan of ale and beer graphically, then you can think of the coordinates, just the positive quadrant, because also beer and ale, so the barrels, number of barrels should be positive. And if we look at the first constraint, so if you look at corn, we know we can use at most 480 pounds. And this is represented by a line. The line represents exactly a mix of the production plants of ale and beer that exactly use the 480 pounds of corn. So if we now look, it should be smaller equal, so we have the area just below it. Okay? Look at the beer, the 0.0, 32, it's exactly the situation that no ale is produced, only beer. Recall from the previous slide. Now, if I look at hops, by the same logic, we have the area that represents all we can produce using hops. And if only beer is produced, then we have the 40 barrels, the point on the intersection of the vertical axis and the blue line. Of course, the third is the mold, nothing really different, so we would create the third region. What is important over here is that the constraints, they should be satisfied at the same time. So how do we do it? We have to kind of put them at the same time, and at the region where they intersect, so it means that they are satisfied at the same time, we get what is called feasible production plan. So in this area, we have a production plan that does not, or that uses the resources, and at the edge uses the resources to full extent. So it will be clear in a moment. We call it feasible production plan. Now the important elements of the production plan are the intersections. So the intersections, the dots, are what is called extreme points, and we can calculate them. The easiest to calculate is the 1, 0, 0. The remaining ones we have calculated already before, 0, 32 on the vertical axis and 34.0 on the horizontal axis. And you calculate all of them by just solving a system of equations. You don't have to do it by hand, but you have to at least understand how this is and how this is done in practice. Okay, so we describe the feasibility, feasible set of possible solutions graphically. Where is the objective function? The objective function can be also represented graphically. So this is a straight line, and the line has the parameters $13 of profit for a barrel of ale and 23. Depending on the parameters, the line will be more or less steep. So the more we are to the right, it means we produce more of ale, we produce more of beer, and because of for every barrel of beer and every barrel of ale we get a profit, positive one, it is increasing to the right. So we have now the line. So looking for the best solution is just looking for the point in the feasible set that is at the most northeast part of the of that set. So here in this case we have the point 12 barrels of ale and 28 barrels of beer. It gives us the profit of 800. Okay, so we can just plug it in and get that we have 800. This is the best you can get in this particular example. So the optimal solution is that what we get. There are some situations that the optimal solution will be not just one point, but there might be many production plants that are optimal. like in the case on the right hand side, I changed here the parameters of the objective function. So the profit from ale is not 13 anymore, but it's 23. So we changed the slope of the profit function, and the entire green area, so infinite number of points, are all optimal. Okay, so this can also happen. Important to know, but this is the way this works. Here maybe just one comment about what is called binding and non-binding constraints. When you take the solution, optimal solution, here the green point, the constraints that are passing through the point, in our case is the constraint hops and the constraint corn, the two are binding, meaning all the resources we had are used to the fullest extent. The blue one, mold, it's not passing through the point. It means there will be some resources left. We don't use all of it, and this one is called inactive or non-binding. How is it solved? If we have the time, I'm of course happy to show you how to use, let's say, software to solve the problem. But how does a solving algorithm could look like? A graphical representation, and this probably helps a bit. So if we start at point 0, we have profit of 0, right? 0 production, 0 profit. Now the algorithm, the way it works, it would calculate the profit, or the value of the objective function, in the two extreme points that are close to it, or closest to it. So here we have the point 34.0. We have a profit of 442, and it also checks that the profit of the point 0.32. The profit is higher for the case 0.32, and therefore this one is chosen. Now we do the same calculation. The next neighbor is the point 12.28, and it improves the profit. So, and it looks for another one. It's lower. It stops over here. So the optimal solution is, this is the way the algorithm works. If you have more complex problems with more than just two decision variables, we talk about the figure, like an object that you see on the right hand side is polyhedron, and the red line shows exactly the idea of the algorithm. So let's do what is important in this case too. We know how to represent it in mathematical terms. We know the meaning of the graphical elements, how the algorithm works. So, of course, also here we would like to see how the sensitivity analysis works. So, the questions that we would be asking is, what if we have more resources? How will it influence the profit? What if the profit structure changes? What if the data is not precise? Well, how will it influence the results? So we can divide it into a number of options, because we don't have so much time, and I see I took a bit longer than expected. I will look at one particular element of the sensitivity analysis, and then move toward the solution in a software. So let's have a look at the first interesting question: is what is the effect on optimal production or on profit if we have more corn? So we have 15 pounds more. Graphically, it means, like, in terms of mathematics, we add 15 to the right-hand side of the constraint. Graphically, it means that we move the constraint up by 15. If we do it, of course, the amount of beer that can be produced, if only beer is produced, is higher. Recall, it's 15 pounds of corn for beer, so we can produce an extra barrel. And of course, the intersection of the two will change as well. For just to understand that we would have a new profit maximizing production plan. The dotted line shows us the profit, and the profit is 815. It means we increase the right-hand side, or we increase the amount of corn by 15 pounds. What we get is $15 more profit. So for every unit of corn, every pound of corn, we get an extra $1 profit. This is what is called the shadow price, and this is something that you can also find in the reports of the software. Here, important to know that the shadow price, you have one shadow price for every constraint. So the same could be done for corn, for hops and malt. And if it's non-binding, the shadow price is 0. Of course, changing something that is not used, increasing, does not change the optimal solution. So the shadow price is 0. Of course, this is, you have to always enjoy it in the context of how much I can change the resources. So how much I can increase the amount of corn or decrease. And this is always a bit more difficult, but the way it's characterized is that how much can we increase the amount of corn so that the solution, optimal solution 12,28, so the one from before, will change. So changing means now we don't produce any ale at all, so it's up. We can increase it to 600, meaning the change is 120, or decrease it by 140. So here what you see is if we decrease it below 340, the point that we had here before, 12.28, or the sort of structure of the solution will change afterwards. So this is what is the allowable increase and decrease. Of course, we can do the same for the objective function. I don't want to take too much of your time, but the same idea holds true over here. So we can ask the question, how much can we change the profit contribution so that the same solution will stay optimal? Here you see that from the profit of 13, we can increase it to 23 or decrease it to 7.67. So the allowable increase would be 10 and decrease 5.33. This is where I really wanted to arrive, because the reason of doing this webinar, I really want to give you something that you can use, and maybe use it in the context of your individual assignment. Maybe you can solve a problem using linear programming, or you can support solving the problem using a decision tree. So luckily we can use Solver. This is an add-in in Excel, so very usual tool, and you can find it in the Data tab. If it's not there, you have to add the add-in. The description can be found behind the link. Of course, I have the slides afterwards, and this is what you will get, but it makes more sense if I really present how to do it directly with Excel. So I stop sharing the presentation and I start sharing the Excel file that you also get. I hope you can see it right now. So now the same problem from the slide we have over here. So in the table above, we have the numbers from the different recipes. On the right-hand side are the profits. The yellow area are the number of barrels produced. If I produce 1 barrel of ale, the profit will be 13. You see it over here in cell I9. There is a function. If I produce on top a barrel of beer, I have $36 of profit. And here you see the amount of resources we used. So we have 1 barrel of ale and 1 barrel of beer. So we use 5 plus 15 pounds. So we use 20 pounds of corn. We use 8 ounces of hops, and we use 55 pounds of malt. Here you just have the numbers. So I have 480 pounds. This is the constraint. 160 ounces of hops and 1,990. So this is actually everything that we need for the model. I removed the ones over here. It doesn't matter, just for you to see that there is the link between the yellow area, so the changing cells, the red area, which is the total profit, and the green area is the resources utilized. If you have a model prepared this way, you can then move towards solving the problem. So you go to the Data tab, go to Solver. I hope you can see it. And this is the dialog box. You have to set the objective. Our objective is the profit that we want to maximize, which is the cell I9. We can maximize it, minimize it, or set a value. An optimization problem could be also minimization, but we have maximization. The changing cells are the numbers of barrels of ale and beer. And we also need to add a constraint. Our constraints are the capacity constraints. You can do it one by one, or you can do it at once. So I put the left-hand side of the constraint are the resources utilized. It's more equal than, and the right-hand side is given by this. I click on OK, and this is what we obtain. This is the prepared solver parameters. Of course, you can find here much more. We don't have the time to discuss it here, but maybe you can play with it a bit. Here, maybe important thing is make unconstrained variables non-negative. This is the case here. And we press on solve. Read really what it says, because it does not always find a solution. Here it found one. All constraint and optimality conditions are satisfied. And this is what is also interesting are the answer, sensitivity, and limit report. I click on OK, and we get the reports generated as worksheets. And the optimal solution is 12 barrels of ale and 28 barrels of beer. The profit, maximum profit is 800. So the report is something that you should have a closer look at. And I recommend to do so. And you find it in the slides. I start sharing now the slides. So for you to understand where they are, you find them in the slides. So the different reports can be seen over here. I don't want to discuss it in detail, because everything that I introduce will be, you can find here. The answer report, from my perspective, is very intuitive, and it links it to the idea of the constraint that you are moving or are binding or non-binding. The variable cells, it tells you here about the shadow price. Recall that the corn, increasing the corn by 1 unit would give us an extra unit of profit. So it's over here. We have also the allowable increase and decrease for parameters of the function, and the same for the constraint. This is can be easily looked at. I arrived at the end of the slide.